start. So I wanted to make two sort of quasi-bureaucratic statements. So the first one is that, well, I mean, the first one is less bureaucratic. The first one is that yesterday I mentioned something to the effect that the commutator of two spinners commute at space-like operations. Completely wrong. You know what I'm saying? It is the anticommutator of spinners that commute. Anticommutator of two these things that have to commute at x minus y square that is greater than 0. Okay? So this is something that you will see in your first quantum field theory book there, but I said it wrong, and I want to emphasize that because ultimately so the thing that I wanted to emphasize with operators that you construct for actually doing observations, they always commute. This is the statement. Okay, but operators that you construct will basically be built from, let's say, some nonlinear combinations of spinners. Okay, that's the first statement. And the second statement is that I forgot to tell you that the attendance has to be taken. So pass it around, and whoever wants attendance can sign it and sign something in for your friends as well if you need. But if you like your friends. But yes. So any questions from last time?
Is for the Spacelike?
Yes.
So we take the x minus y equals
X minus what?
It might be like a Spacelike condition for the.
Right. So this is, so I'm always working with minus plus 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 signature, right? So that means that if this is sufficiently positive, I am in the space-like part. Fine? So if, so this is in, if we have chosen a signature here. So with this signature, x minus y square greater than 0 is the condition for space-like separation. So, so that's just a minor comment, but, right, so what we want to do today is we want to kind of use all the ingredients that we discussed last time and until now, and derive the thermal density matrix for the Rindler observer. Okay, so we said last time that an accelerating observer is what the natural geometry that you can associate to an accelerating observer in Minkowski space is Rindler metric. And we also said that the Rindler metric, by natural analytic continuation of Rindler metric, you can get to all 4 regions of Minkowski space, and Minkowski space is essentially a Kruskal construction starting from Rindler wedge. Okay, so that is the point, and so let's start there. So let me just briefly remind you what Rindler is. So this is our metric, okay? So this means that rho is greater than 0, and the reason why rho is greater than 0 is coming from the fact that this is in Lorentzian signature, there is a horizon here at rho equal to 0. Okay? So rho greater than 0, which in other words, it is rho is part of this. And we also have this in, okay. So, and eta is lies in the real line. So this was a coordinate chart. Okay? And we also defined a new coordinate system, which was this. And rho sinh eta. Hopefully my signatures were the same as last time. And if this is the case, hopefully the signature will be correct. So this is what you get for Minkowski space. But the point is that because of these conditions on the coordinates in Rindler, you will have the condition that x square minus t square has to be greater than 0. And in other words, x is greater than 0 and t is less than x. Absolute value of t is less than x. And this region is what we call the Rindler wedge. Okay? So this is the region that we chart by this coordinate system. Is that fine? So now I start, last time I used Rindler as a crutch for computing the temperature of a black hole because the Rindler coordinate system is related to the near horizon metric of a black hole. Okay, that's what I did in one of the lectures. So, but I can also compute the temperature associated to Rindler. So Rindler itself is a prototype for many of the things that we talk about. There are some subtle and important differences between Rindler and black hole geometries, which I think are still not fully appreciated. But at least at the very basic level, if you think of it in terms of coordinate transformations, it is the fact that Rindler is connected to Minkowski is in many ways a prototype for how we think about Schwarzschild is connected to Kruskal. And more generally, black hole exteriors are connected to black hole interiors. Okay, so because of that, we will study basically Rindler first as our starting toy model, and it's a toy model which is where there is no ambiguity about whether the principle of equivalence holds here. So in some sense, all the questions about the structure of horizon, etc., are statements about whether in these lines, when you apply to a black hole, whether principle of equivalence holds. So that's what really, in many ways, that's what the information paradox is really about. Okay, so but here, on the other hand, there is no ambiguity, because we know for a fact that there is nothing special happening here. It's just an accelerating guy's trajectory, and this is some kind of observer-dependent horizon that just happens to be visible to a trajectory. So there is no ambiguities here. So we expect everything to work very well. So this is good. This is a good prototype. So let's define what is called the unroot temperature by doing the exact same thing that we did for when we used Rindler as a crutch for black hole temperature. Okay, so there we essentially did the same thing before, but I'm just elevating it to a calculation applying for Rindler directly. So what unroot temperature is a name given to a temperature experienced by an accelerating observer, accelerating trajectory sitting here. Okay. So that's what this is. And the natural way to associate that to Rindler is by our previous trick is to consider the Euclidean continuation of this. And we can write down a Euclidean metric, which is rho square d eta square plus d rho square. Okay, so now this eta is, I'm thinking of it as a complex or an imaginary or an analytic continuation of that eta. So I was kind of debating whether I should call it eta or phi. It's a little bit better to call it phi, because then it is immediately clear that the periodicity is 2 pi. So, but let me call it eta because there are various places where it's less convenient to use phi. Okay, so this is our Euclidean metric, and it's immediately clear that if you want to avoid a conical defect at rho equal to 0, avoid conical defect or an excess at rho equal to 0 implies that eta has to be periodically identified with a period of 2 pi. Okay? So this means from our previous argument, philosophy, that temperature that one should associate to Rindler is TR is 1 by 2 pi. Okay, so this is the Rindler temperature. So Rindler is in some sense the simplest example of a finite temperature geometry, and the claim is that we associate a 1 by 2 pi to this. Okay, so this is sort of what you should kind of think of this as the as kind of like a metaphysical temperature that you're associating to this entire geometry. Okay, but physically, an accelerating observer that is sitting here, what he would see is so the idea is that let's consider so the physical temperature, physical temperature experienced by measured by an observer, an accelerating observer, at rho equal to rho naught, is that you can compute because we know that we need to know the proper time basically, right? So this will be at rho equal to rho naught. This is going to be your proper time, and since the temperature is associated to this Euclidean continuation of this eta, the natural candidate, so eta going to eta plus 2 pi implies that your tau, which is basically this proper time, has a periodicity of fine. Okay, so this is the periodicity in the proper time, and that means that the associated temperature for a guy sitting at rho naught is basically 1 by 2 pi rho naught. Okay, so this is the physical temperature measured by a trajectory at some particular point. Fine? If you actually had a thermometer, that's what you expect to measure. So because what you actually measure by a person sitting at, what you measure is depending on your trajectory in special activity, right?
Basically, a thermometer has to get kinetic energy from bouncing molecules.
Exactly, yeah.
So what is bouncing?
So no, it's not the bouncing so much, the time that is measured by him, because he's accelerating, right? So because he's accelerating, he's pumping energy into the system, and so any kind of couplings that you make in your system. So that's what always proper time means. Proper time means that you are coupling your system to, let's say, electromagnetic field. So the natural time scale that is set by this tau. That's the claim. So which means that the velocities of your particles will appropriately get accelerated. Okay, and note that this is an accelerating frame. It is not a uniform velocity frame, so it's not special activity.
So what is pumping in this energy?
Because you're accelerating.
It's a vacuum solution, so there is energy.
No, it's not a vacuum solution. Because if you're an accelerating particle, you have to accelerate somehow. You have to have energy coming from somewhere. So that's why this is an idealization, right? So you're in some particular location where you're sitting there and accelerating, and if you want to indefinitely accelerate, you have to have infinite amount of energy. And that's what is heating up the system. And that's how you measure some, basically you will experience a thermal bath of radiation. And by thermal bath of radiation, it can be anything. It can be like, what it really means is that if you were to couple your system to any, let's say, field or particle or anything, this is the temperature that you'll experience. Okay, so that's what this means. So if you don't have any way of coupling to anything, there is no notion of temperature anyway. See what I'm saying? So whenever you say that there is a notion of temperature, what it means is that you assume that there is some mechanism that you have for coupling your system to some external, external system, any kind of external system for that matter. So that's, So I mean, the notion of what, a detector is, etc., etc. I mean, you can develop more, but this is, for making our statement, this is more than enough. Okay? So this is our temperature. So, and of course, this is actually, we believe that this is actually a measurable, observationally measurable quantity. But this is in Minkowski space. So all of those those questions are fundamentally what give rise to, for instance, in the case of black holes, right? So in the case of black holes, these are like the fact that if you can stay right above the black hole, that is what is going to take you energy. Okay, so and then there is a question of all of these are questions that one will have to contend with if you really want to make a statement about what it means to hover above a black hole, because you are doing work against its gravity. So then you have to worry about all these questions. But I'm saying that a uniformly accelerated observer is an idealization fundamentally, right? So, but it is also to be said that you can do a finite version of this calculation where you're accelerating only for a finite amount of proper time, and you will see that you will see a profile. You can actually make it very precise. There can be, you can couple it to a, what is it called, actually an Unruh detector. That's the technical name for it. And you will see that this detector will actually tick, because of the fact that you're accelerating. So, of course, making it an experimental thing, it has not been done. But if Unruh were to live long enough, and this experiment, he'll have to live really long, unfortunately, I think. But this is a remarkable result. Okay, so because it basically just means that if you accelerate an empty Minkowski space, and it can be even for a finite amount of time, you will always produce this thing. You can compute this by putting in back the various Boltzmann constant, all of those things, and compute what the actual temperature, and you'll see that it is almost immeasurably small. But the point is, it is expected to be physical, even in standard Minkowski space, and even for finite duration acceleration. Okay, so, but we are not interested in finite duration thing. We are interested in this idealization of a uniformly accelerated observer who has a horizon here. Okay, so that's what we are interested in. Yeah. Which analysis? Why we are doing this in temperature? So essentially because we attribute temperature whenever we have a periodicity in the thermal direction. That's what we expect from standard Euclidean field theory. This is what we were discussing a few weeks ago. So, and here what we are saying is that, is there a natural temperature that one can associate to the Rindler horizon? That is the question. And so the natural thing to do, based on what I said about Euclidean continuation, we'll make it more, let's say more, add more material to it today. But at the very basic level, you expect that if there is a Euclidean periodicity, then there is a notion of temperature. And here we are saying that there is a natural periodicity that one can assign, because if you go to Euclidean signature, then you have, this periodicity is necessary for that the geometry doesn't have a conical defect. So because of that, we say that, okay, this is the natural temperature that the system has. So we'll have more to say about it. This is like something that so the question of absence of conical defect is really a statement about principle of equivalence in Euclidean signature. So what we are saying is that the tip of the cone is also a regular point. So that's a statement about the Euclidean regularity of the horizon. So again, we are assuming that the horizon is smooth. That's what we are really doing even in Euclidean signature. Okay? So if you assume that the horizon is smooth, you will always manage to get temperature in some form or another.
Why is there a significance of minus there? Beta minus is.
Well, I mean, okay, so in Euclidean signature, I don't really need it. I can just do this. Okay? So I was thinking more of this when I wrote it. So, but yeah, so either way it's fine. So because, so the interpretation is that we are thinking of this as the actual physical temperature experienced by an accelerating person. Yeah. Right. So the point is that, see, given a Rindler wedge, there is no unique acceleration. Right? Every value of rho here corresponds to a different accelerated observer. And this rho is controlled by the acceleration of that trajectory. So on this trajectory, this rho is constant. So if you remember our previous Penrose diagram, so this is what we had, right? So we had these slices or foliations where this eta was like this, these guys, and this rho was, constant rho lines were these. And these constant rho lines are basically accelerating trajectories. So the point is that what we did when we constructed Rindler coordinate system, if you remember, which was a couple of weeks ago, is that we are using the proper acceleration of the observer as his coordinate, as the coordinate that he is living in. Okay, so it's a choice we are allowed to make. And that's what we are using here. So when you say rho is constant, it means that his acceleration is fixed on that trajectory. So that's why it's a uniformly accelerating trajectory. Okay? Any other question? Yeah.
Does it make sense to associate temperature with non-compact?
So all of these are somewhat technical questions. So this is clearly an idealization. So that's what I said, that infinite acceleration is not possible, because that requires infinite energy. And even in a finite universe, that's impossible. So what we are talking about here is all about, so that's why I specifically said that if you have a finite range of time, you can still measurably, at least in principle, if you had enough experimental cojones, you would be able to actually measure it.
Okay. This is not a quantum effect, this is
That's, so let me, this is a quantum effect in a fixed space-time. This is not a quantum gravity effect, but this is basically, you will need to quantize the fields in order to see this. Yeah. Yeah. I mean, it's basically a change of frame that gives you that. Yeah. So, I mean, this is I'm surprised if you have seen Bogoliubov transformations, I would have expected that you would have seen it, because this is the the most basic version of Bogoliubov transformation. So, but I'm not going to quite do it in that way. I'll do it in a slightly different way. But but let me not use words that I'm, at least at the moment, not going to use. So, yes, so what we want to do is we want to kind of do this. So this is sort of the primitive and the most simple way to show that Rindler has temperature. So what we are going to do now is we are going to kind of, do this in increasing sophistication or increasing abstraction and learn a few more things. So that's what the goal of this lecture is, okay? So let's start. So the first thing is we are going to do this more systematically using path integrals. Path integrals for unroot. Yeah, so what we would like is that this, so here what it means is that if you have temperature, you expect that there is some kind of a density matrix. Okay, so yeah, so this will again be a kind of a general message. So here you notice that eta is a time translation isometry. Okay, you can shift eta, and that's a symmetry of the space-time. So that means that there is a conserved charge associated with this, which we will call H eta, is the conserved charge that generates conserved charge or generator that generates eta translations. Okay, I'm not committing myself to any specific field theory yet, but just the fact that there is a shift in the symmetry, I'm going to look at theories which respect that symmetry. If I write the scalar field theory in this background, it will have this eta translation symmetry. Okay, and using that theory, I can always write down a Hamiltonian in this form. Okay, corresponding to this translation. So this is a basic claim, and because of the fact that so if you have a thermal, if you have temperature at this TR, which basically corresponds to, let me write, beta is equal to 2 pi. So this means that my thermal density matrix is basically nothing but minus 2 pi H eta. Okay, so this is the Unruh or Rindler thermal density matrix. And we want to derive this. So this is what we expect from our sort of this hand wavy calculation. Okay, it's not a true hand wavy, even though this looks kind of very primitive. So what we'll do is we'll basically try to derive it in a few different ways. So this is what we'll do. All right, so what do we have? So we want to understand this. So we want to, or we will argue that this is the density matrix, is the reduced density matrix of Minkowski vacuum on the half line. So all of those statements we will make it precise. So whenever you have a field theory, the field theory has a vacuum. Okay, a vacuum is not a property of the space-time, at least when we are working with field theories living on space-time, it's a property of the field theory. Okay, the space-time is just a metric. You have some scalar field theory on that manifold, then you compute the Hamiltonian of that scalar field, then it will have a vacuum. Okay, so if you write down some theory on it, then you can associate a vacuum. If you write down a theory in Minkowski space, let's say scalar field theory in like your Sretnicki and so on. So there is a vacuum state. The vacuum state kind of plays like a kind of a tangential role in many of those discussions, but for us it will be important, essentially because the vacuum will tell us the most important things anyway. So the vacuum state in Minkowski space, when you say vacuum state in Minkowski space, you should always have a theory in mind. Okay, it's not a property of the geometry. You are always assuming that there is some vacuum, let's say of scalar field. And typically we will think of scalar fields. Okay, so that's what I mean by a vacuum. So if you have a scalar field in Minkowski space, you can write down a vacuum, which is this, which you have all seen, which is basically you do a mode expansion in terms of A's and A daggers. This is the thing that is annihilated by all the A's. Okay, so and this guy is what we call the ground state, the Minkowski vacuum. And the second ingredient in that statement is that if you have Minkowski space sitting here, T and X, so what I mean by a half line is, let's say I'm just talking about T and X, forget about Y and Z and all that, you can add them. Y and Z don't play any role. Okay, so if you have Y and Z, you will still only be talking about half line. So which means that all the other Y's and Z's we are talking about, it's like half of the space-time. That's how you should think about it. Okay, so what I mean by so the statement is that if you have a pure state like this, you can also write down a pure density matrix of this form. Okay, so this is the Minkowski density matrix. This is the density matrix corresponding to the Minkowski vacuum. It's a pure state. I just wrote it as a density matrix, that's all. So now the claim is that I want to split the space into two halves. Okay, I want to split the space into two halves, and this half is, this is where my Rindler wedge is living. I'm looking at, note that kets are generally speaking associated to spatial slices from our discussions before. So you have a ket, and what we are thinking of is we are splitting the space that the theory is living in, the spatial slice of the theory is living in, into two halves. And this part, which is called x greater than 0, let me call it, I think I called it A here. Yeah. And this region, x less than 0, is basically B. Okay? So the claim and so one of the prejudices of quantum field theory, it's not quite a prejudice, I mean, you can make it somewhat more precise, but it is one of the intuitions of quantum field theory. It's not a prejudice. It's one of the intuitions of quantum field theory is that the state can be broken up into pieces. Okay, so this is an important piece of the intuition about the states in quantum field theory, or the Hilbert space of quantum field, not Hilbert space, the eigenstates of quantum field theory, which is not often emphasized, but which is true and generally believed. And that belief is that you can think of the Hilbert space of a quantum field theory very crudely as a set of lattice sites. In some ways, this is completely wrong, okay, but intuitively this is true. Okay, so instead of a spatial slice, you think of your Hilbert space of the quantum field theory as, this is the point is that you're associating a Hilbert space to a spatial slice in quantum field theory. That's the reason why we wrote down this field configuration as the ket and everything. Okay, so given a spatial slice, you can associate a Hilbert space to it in quantum field theory. So, but I'm saying more. I am saying that the Hilbert space can actually be split up into pieces corresponding to subregions on the spatial slice. Okay, so for instance, this is, let's say, this is my intuition. So, which is that I'm going to split this Hilbert space into a half which is on this side and another half which is on this side. Okay, so there is no particular meaning to these lines that I just drew, but I'm just trying to split it into two pieces. And this is something that is familiar, for instance, from let's say spin systems, like I don't know, what is it, your favorite Ising model. So Ising model, for instance, has on each lattice site, right, you have a spin sitting there. So this is basically a two-dimensional Hilbert space. A spin is basically just a two-dimensional Hilbert space. Okay, a spin up and spin down. So this is the minimal Hilbert space that you can have, which is non-trivial. That's what a qubit is. So a qubit is a two-dimensional Hilbert space. So if you put a qubit, a line of if you think of your Hilbert space as being built from tensor products of these qubits, then you have some notion of a Hamiltonian where interactions are local. Those are kind of important words. Okay, and this is sort of I don't know whether it has. So in quantum field theory, these things are not emphasized, but these are very important facts. Okay, so an Ising model, for instance, if you remember, Ising model is basically a Hamiltonian like this. Okay, whether this is I and this is I plus 1, and then you have a sum like this. Okay, so what this is saying is that you have an interaction of the ith spin with a spin sitting next to it. Okay, so when you have an interaction term which is adjacent, then you typically say that your Hamiltonian is local. Okay, I think this is something that I have told at least some of my students multiple times. So you might be a little bored, some of you, for instance. So, but the thing is, for a quantum field theory, this is the same intuition that we adopt. Okay, so the intuition is basically that you can split the system into two pieces. This is in some sense completely wrong, because field theories do not have this kind of, you cannot latticeize space-time in Lorentzian field theories. There are fundamental obstructions to it. Okay, but nonetheless, this intuition itself works. Okay.
But local necessarily means that equation should be with the immediate.
In field theory, that's not very important, right? So when I'm using an similar, analogy, I'm calling it like adjacent, but it doesn't necessarily have to be. It can be like a few of them, etc., etc. So the only point about field theory that I want to really take away from here is that there is some notion of closeness, and if the theory that I'm considering, the interactions are between adjacent points, or essentially on the same point. That's what it really means to say local field theory. So in the analog of in quantum field theory is the fact that your scalar field basically interacts like this, right? So this is your theory. So where you're integrating, and note that this is an integration in space-time and everything is defined on the same point. Okay? So there might be derivatives. So derivatives you should think of as some sort of building some adjacency. Okay, so because you can always discretize a derivative by taking xi minus 1, whatever. So, and this is the idea. So the point is that local field theories are defined as integrals on spatial points. There is no x and y. Okay, so that's the reason why this is a local theory. And our intuition, and there is, for various purposes, you can think of field theories as kind of splittable into subregions. Okay, so that's what I'm doing here. I'm doing the most primitive split on a spatial line, on a spatial slice, which is to split it half this way and the rest. Okay, so I'm only splitting in one of the directions. I'm not splitting in x and y. Y and z are basically it's just a half plane, all of them. So only the x will matter for my discussions. Okay, so this is the split I'm doing. So now the claim is that this density matrix that I found here, let me call it Rindler. So the claim is that trace over B. I mean, so associated to this region, I will claim that I have a Hilbert space HB, and associated to this region, I'll claim that I have a Hilbert space HA. And this statement is technically actually false for quantum field theory, but it will work for our purposes. Okay, in the sense that you can't really split a Hilbert space of a quantum field theory into two pieces like that. It cannot be tensor factored, but all the calculations that we will do will be consistent with if it were true. So there is so there are more things to be said here, but that doesn't matter for our purposes. So what I mean by, so the claim is that this Rindler Hilbert space is basically this guy. Okay, so the Rindler Hilbert space associated to the right wedge A is basically this trace over B of the Minkowski vacuum state. So it's a reduced density. This is what you mean by a reduced density matrix. How many of you have not seen a reduced density matrix? Anybody else not seen one? Okay, so a reduced density matrix is, I have some Hilbert space, I tensor factor into two pieces. This is called tensor factorization. Okay, so that's a word that is useful to kind of remember. The tensor factorization basically means that you think of your total Hilbert space as built from two or more tensor factors. So for instance, in this case, if you associate a tensor factor here, this is basically, something like this. So this is what I call my Ising Hilbert space. Okay, so tensor product of all the Hilbert spaces sitting at each point. Okay, and each of these things is a qubit Hilbert space. Right, so this guy, so this is what I mean by splitting up the Hilbert space. In quantum field theory, it's not technically quite true to work in terms of Hilbert space pieces, but the same idea works if you work with, what are called algebras of observables. So we won't really make this distinction, and for our purposes, space-time can be split into pieces like this. Okay, so this is the claim, is that this is my Rindler density matrix. So this is what the claim is. Okay, so right. So what we want to do, so now what we want to do is we want to compute. So essentially what we want to do in this way of looking at it. So this is my first claim, okay? I'll calculate, I will motivate it further. We will do it in different, multiple iterations today. So the first iteration is that I'm looking at my space-time. I think of the space-time as with a cut here, okay? So my density matrix, so the claim would be that what I want to compute would be, let's say, so I specify my fields here and fields here. So I'm trying to go and define this. I told you before that density matrices can be computed using path integrals, right? So, and in order to do that, so if you want to compute a path integral, some form of path integral calculation I want to do here, I have to first specify a phi 2 here and a phi 1 here, and the density matrix would be this object, right? The density matrix element would be something like this. I have to specify. If I don't specify, it will be just a density matrix which is an open cut, or two open cuts there. So the question is, how am I going to compute this, right? Because if I'm just looking at Minkowski space, I didn't tell you how to compute these density matrices unless the cut was across the whole space-time. Okay? So, and this is where what I mentioned earlier about identifying the time translations becomes useful. So there are, spacetimes can have multiple time translation isometries. And here, this metric that I wrote down, which is my rho square d eta square plus d rho square, where rho is this guy. This has an isometry in the eta direction. Okay? Yeah. Continuity means?
We didn't specify two different values on two different sides. We assumed that.
Okay. So I think you're talking about a picture like this, maybe. So where I specified something at some particular point, right?
Drawn an arbitrary cut somewhere.
Yeah.
Things would be continuous.
So what if I have a cut on a spatial slice, there is no path integral above it, right? So this is a strange object from that point of view. So if you know, in the pictures that I had earlier, I always had let's say some spacetime was like this, and I cut it, and then there was nothing above it.
Yeah, in the sense that when you wanted to glue two spacetimes,
Yeah.
it was the same boundary condition.
Yes, but I'm not gluing it here.
So it's actually a term.
Yes, I mean there is these. I'm not so if I declare that phi 1 is equal to phi 2 and integrate over that phi, then I would have sewed it together. Okay, so if you remember, like when we had a ket and a bra and so on, so if you had two, you know, let me just draw that picture one more time. So this and this, where the data was unspecified here and the data was unspecified here. Here, this was the time direction, and here this was the time direction. Okay, so then what I do is this, I specify a field here, I specify a field here. Well, I mean, I can call it phi 2. Then I say that phi 1 and phi 2 are the same, and then I integrate over phi 1. Then it becomes this. Okay, so that's the thing that we have. That's the thing that we have here. So, but that's not what is happening here. So what is happening here is that I have put a cut in space-time, and I'm saying that the value of the field configuration on this side of the cut is phi 1, and the field configuration here is phi 2, and my goal is to somehow evaluate this density matrix. It's not obvious from what I have told you so far that this can be a calculable object, right? This is not clear because I have only told you how to cut it all the way across. Okay, and I also told you that if you wanted to compute a path integral where this cut and this cut were unspecified, that basically becomes a density matrix. Okay, so and that was because of the fact that there was a time evolution in this direction. But if I do a cut like this, I cannot, if I have a time evolution that takes me from here to here, I can still do the path integral. And that's the thing that gives me the untrue effect. Because this eta here is in Euclidean signature, it's actually a rotational symmetry. Okay? So if I have a rotational generator, I can use that as my Hamiltonian and do my path integral, and you will end up finding the reduced density matrix. All right? So this is the story. So that's what we are going to do, and yeah. So from this point of view, this is nothing but e to the minus 2 pi h eta phi 1 phi 2, right? So this is my the density matrix that I want to compute. So what I'm going to do in the momentarily, let's say, is I'm going to compute this same exact matrix element using path integrals. Okay, so yeah. So but before going there, I want to make a few statements about what this generator is once you go to Lorentzian signature. So here it is clear that this is a rotation, right? Eta is basically just another name for phi. But if you go to Lorentzian signature, if you remember from last time, you had this eta translations, we identified them as boosts because of the rho cosh eta and rho sinh eta. Okay, so this in Lorentzian signature is what is a boost generator. So the boost generator is going to play a crucial role in our discussions. So let me digress for a minute to talk about it. So this is, we'll call it, let's say K. It's a standard notation for boost generator. Okay, so any questions? Yeah, sure.
Will path be like this, or will it be like you're identified it and then a circle into this?
You mean like am I identifying these two things?
Not identifying.
Uh-huh.
I mean the path you've drawn is going on the board. Should actually be going like this. Because you have to go through time.
This is the time here, right? Eta is the Euclidean time. So I am integrating it along the space. The integration is the space over where my field lives is on this plane, with a cut here and unspecified, or field configurations phi 2 and phi 1 specified at the cut. So I am going to integrate. Now the idea is that, so the reason why this particular path integral is doable is because there is a natural time translation generator in the eta direction.
Which way is time and which way is space?
This is the way in which it is time, and space is radial. Okay, so this is my rho, if you like, and this is my phi. This is just the the split of this is just polar coordinates, right? This is just polar coordinates. Rho, eta if you call it phi, but eta has to be thought of as somehow time, Euclidean time. So that's why I'm not calling it. It's, well, I mean, see, the cylindrical quantization, the radial direction would be the time, right? That's radial quantization. Here, that's not what this is. This is the angle direction here is the time direction. Okay, so this is this is really and this particular path integral is doable only because boosts are a symmetry of Lorentzian theories. So when you go to Euclidean signature, mixing rho and eta is actually a symmetry of the theory when you work with x and t coordinates. Okay, so and because of that, we have this property that in Euclidean signature it becomes a rotation. And because it's a rotation, that rotation you can use as your Euclidean time translation guy and do your, determine your density matrix element by computing this object. So this h eta, this eta is an index. It's not h times eta. So I am moving by an angle of 2 pi using my h eta generator. Okay, so that's what I'm doing.
In the previous density matrix calculation, we had the time of beta, right? So that beta is replaced by 2 pi.
No, but so for Rindler case, beta was 2 pi.
Yes.
Beta was 2 pi. So that's what I'm using. I'm using it specifically for Rindler. But of course, the same kind of calculation in principle one can do elsewhere as well. But elsewhere means in the case of Schwarzschild as well. But in the Schwarzschild case, it will not be that straightforward because the external Schwarzschild geometry does not have a boost isometry. Okay, but the point is that in the near horizon geometry, there is an emergent boost symmetry, if you like. Okay, so that's what, and it's basically related to the fact that the horizon, again, fundamentally everything is related to the fact that you're assuming that the horizon is smooth. So because horizon is smooth, at the horizon, space-time is like Minkowski space, and in Minkowski space, you can always Wick rotate and go to Rindler wedge, and there the boost basically becomes this, right? So this is the story. So, any other questions? Okay, so the claim that we will make, let me make that claim a little later. So let me make a digression to talk a little bit about boost generator in case you have not heard it at all, or even if you have heard it, maybe not the right things may have been emphasized. Okay, so we want to take a digression about boost generators in Poincare invariant theories. So, and the first observation is that boost is always a symmetry in Poincare invariant field theories. Okay, so if you have not seen the Poincare algebra, how many of you have seen the Poincare algebra? How many of you have not seen it at all? You've not seen Poincare algebra? So that makes things a little difficult. So I think so I'll just make two statements very quickly. One is that in any quantum theory is basically defined by the Hamiltonian and the set of operators that commute to the Hamiltonian. That's how you essentially define a quantum theory. Okay? So, and in the case of Lorentz invariant quantum field theories, there are 10 such operators. 10 operators which commute with each other, or it's 10 operators which are significant for this discussion, one of which is the Hamiltonian. Okay, so operators that will commute to the Hamiltonian are interesting for various purposes. And in the case of Lorentz invariant theories or Poincare invariant theories, there exist 10 such operators, and those are basically what we call the Poincare charges. Okay, so momenta, rotations, and boosts. Okay, if you count them, you will find 10. Okay, so and those 10 operators, I'm going to call them J mu nu, P alpha, and that's basically it. So this is 4 times 3 by 2, and this is 4. Okay, so that gives me 10 generators. So there are 10 such operators which are special in any quantum field theory. Whenever I say quantum field theory, I'll always mean Lorentz invariant, Poincare invariant quantum field theory. Okay, in any Poincare invariant quantum field theory, there will be 10 such generators, a guarantee. So all the theories that we talk about will have these. Okay, so and how they are constructed from the basic fields of the theory, like a scalar field or whatever, is not our concern so much. But they can always be constructed. Okay, so for instance, if you have a scalar field theory, you can use Noether procedure, various other things in order to explicitly construct them. Okay, if you have a Lagrangian, etc., etc. But even if you don't have a Lagrangian, these operators must exist in a Lorentz invariant, Poincare invariant quantum field theory. So these, and the point about these operators is that because of the symmetry, so the symmetries, you know, I'm sure that you have seen rotations basically translates to generators, you know, having some kind of algebra, right? So that I think everybody must have seen. So similarly, here, these guys will also satisfy some algebra. And that algebra, I'm not going to write it in great detail, but I'll schematically write this guy as, you know, so there are some various indices and various combinations. We don't really care, especially about this particular one, we don't care. So there are 4 terms here, okay, where eta is the Minkowski metric. Okay, so the commutator of 2 of these boost slash rotation. These contain the boost and the rotations. When mu is 0, so we call, so mu, you know, mu and nu can take values from 0 to 3, right? So these guys and these guys are the independent generators there. Okay, and these are basically rotation generators, some slight redundancies there, and these are the boosts. Okay, so and if you have so the commutator of these Lorentz generators, these are called Lorentz generators, and they contain boosts and rotations, and these Lorentz generators have some algebra like this. And then the more interesting one for my purposes is this one for the current discussion, is that, so that I will write a little bit more explicitly. Okay, and the final one, if you want to see that, is just the fact that momenta commute among each other. Okay, so this is the full Poincare algebra. Which one? Yeah, I think it is mu alpha beta. Okay, so that's my algebra. So this is the algebra that I'm going to focus on for the moment. Okay, so and the reason why I'm interested in that is because boosts are a special class of conserved charge. Okay, it is unlike, even for people who may have seen the Lorentz algebra, this may not have been emphasized during your QFT course. So the point is that, so it's a little too quick, but I said everything that is really necessary. You know what I'm saying? So if there is any question, you can quickly ask. Is that okay? So there are some generators and they have some algebra, and that's essentially all that matters for our purposes. Okay? So the point is that these p mu's are momenta, and they are the charges that generate translations, and translations are a symmetry of part of the symmetries of Poincare. So in particular, P0 is the energy, which is sometimes also called Hamiltonian. Okay? So this is our main object, and the key point is that, you know, or key point, or one thing that you might, from that equation here, you can check that because when this is mu is 0 and alpha and beta are I and j, this right hand side is always 0. So this is nothing but the statement that angular momentum is a conserved quantity. Angular momentum is basically the generator of rotations. Angular momentum is a conserved quantity. Okay, so that's the first observation. But what the next observation is that this state, on the other hand, if you compute this for the boosts, you will find that it is not conserved. Okay? So the Hamiltonian doesn't commute with the boost generators. So that might seem a bit surprising, because what you really want, when you say, my statement that there are, I started with the statement that somehow there are 10 conserved charges in a Poincare invariant quantum field theory, right? So when you say conserved charges, what you typically mean is that the thing is under time evolution, it doesn't evolve, okay? So and time evolution is usually determined by how it commutes with the Hamiltonian. So angular momentum commute, and trivially you can check from the p mu commutator that all the other momenta also commute. But the boosts don't seem to commute. Then why do we call it a, Poincare invariant quantum field theory, Poincare invariant quantum field theory? And the answer has to do with the fact that it's not just the commutation relation with respect to H that decides whether you have a conserved charge. You really have to pay attention to the full Heisenberg equation of motion. In other words, Heisenberg equation of motion basically says that the full evolution equation has this form. Okay, so the total time derivative also contains a partial derivative. Okay, and now the claim is that if you want to compute the total time derivative of the boost generator, you will have this plus d of this form. Okay, and the claim, so we can check that. So if d0 j0 I is pi, then this guy will be conserved. Okay, and it turns out that this is actually true. So for instance, for scalar field theories, I'm going to ask you to check that as a, sorry? There is an I? Yeah, there is a, so there is a D0. So see, H commutator J is IPI, right? So if I have, oh yeah, so I think here there is an I. So yes, so that's the one that is easy to remember. But here, this, if my commutation relations based on this and that, you can fix this. So there is a, so what I think this is correct. So the point is that, but there exists a choice of this form. Okay? So, and this is why boost is basically a conserved quantity. So the claim is that this is supposedly true. This has to be true. And how do you show that this is true? So we'll not do it in general. What we'll instead do is we'll, so let me write down the Noether charge of Lorentz generators. Okay, so in particular, let me write down L0I, or what did I call it? I called it J0I. Okay, so this, I will write it this way. So the claim is that Noether charge of boosts is of this form. So this is something, again, I mean, if you have, maybe you have seen it in quantum field theory how to compute Noether charge. So, but it turns out that this is the case, where this J mu nu for a scalar field theory, again by Noether procedure, is obtained as this. Okay? So again, if it was a bit too fast, so I'm not, so the statement is that any theory has basically conserved charges. Any Lorentz invariant quantum field theory has conserved charges, and the boost charge can be written in this specific form, where xi is the spatial coordinate, t is the time coordinate. All of this is in Cartesian coordinate system, and this g mu nu, this j mu nu is basically the Noether charge associated to a scalar field for associated translations or Poincare transformations, if you like. So this is something that you can just believe it from me, or you can derive it. And the claim is that if you take this definition, you see that there is an explicit time dependence in T, right? So, and that explicit time dependence will basically kill off, is what will give you the correct PI dependence, and will kill it off. Okay? So this is kind of a small exercise, and if you're not familiar with these things, it's a good idea anyway to know about Noether charge. Noether charge is probably one of the most important things in quantum field theory, okay, at least in the QFT 1. So if this, you can treat this as an exercise, but the only thing that we want to take away from there is that boosts are a symmetry of point-correct quantum field theory, and explicit time dependence in the charge plays a role in interpreting that as a genuine charge. Okay? So unlike in the other charges, this T dependence is an important ingredient. So these are the two facts that we want. Okay? Any questions? I mean, you can, so let me not, I don't want to get into it too much, but you can think of it as the overall center of mass if you go to a non-relativistic limit and so on. Overall location of the center of mass. So like, yeah, so it's, you can work it out, but it turns out that, yeah, there is indeed a conserved, that's a good question, but it's just that it's too much of a distraction for us to get into it. It's, so what you're asking is what is the conserved charge, what is the quantity that you can associate to it? So, and the answer is basically, roughly speaking, the location of the center. It's not a very interesting quantity, that's why people don't talk about it. You know what I'm saying? But you can work it out systematically. So anyway, which algebra? What do you mean it's not closed? I mean, it's part of the point-correct algebra, right?
But like taking one commutation is not producing the third boost, but some rotation also will be.
Yes, that's true.
So it's not in that sense.
Yeah, but that's not going to play a crucial role for us. Yeah, it's true. It's true. It's so the right-hand side of yeah, so it's true. So, but I don't have anything much to say about that. Yeah.
Rotation on an energy eigenstate would give another energy eigenstate.
Right, that's true. Right.
The interpretation here is you won't use the same energy eigenstate.
Yeah, so this is, so that is essentially kind of related to the fact that this is my commutator, right? So I'm talking about the fact that I really need to time evolve, and the explicit time dependence of the guy will matter for interpreting that as a conserved charge in the total sense. That's what I'm saying. So yeah, so I mean there are various statements one can make, right? Yeah. So let me not make any of them, and so yeah, I mean, so this is if you're I'm glad that you're intrigued by it, because nobody talks about boost ever, right? But boost is genuinely a conserved quantity in the sense of this, but yeah, there are many things to say. But so let me just make one statement, which is that one of the reasons we don't really care about boosts is really partly because of the fact that, okay, so the primary reason why we care about, in principle, boost is actually a good charge, because I think one of the things that, for instance, some of our friends sitting here will talk about is that you can work with eigenstates of boost instead of eigenstates of, let's, for instance, say momenta. Okay, when you're talking about the Hilbert space of a quantum field theory. So this is something that, it's kind of an active field of research, let's say. But yeah, I mean, if you're interested, you can take a look, but it will not play any role in my discussion. So let me not get sidetracked into this. So, but yeah. Okay, so let me draw one picture about what boost does, in t and x coordinates. So this is my so note that boost is, the time coordinate will basically get moved by boost like this. Okay, and the one thing that I want you to notice is that if a time slice is getting moved up like this on this side it is getting moved down like this, and that will be important for us. Okay, so if you want to interpret this on the right Rindler wedge, we said that eta translations are moving you upward. This is basically the eta time coordinate, right? So by moving along eta, I am moving along these constant eta slices. So, but the natural continuation of that on the left Rindler wedge is not going to move you this way, it's going to move you this way. So that is something I want you to remember because it will play a role. Okay? So, yeah, I mean, I'll also write. Let me also write the boost generator for a massless scalar field. This is I'm just plugging in this expression into this for a massless scalar field and writing an explicit expression. So note that these integrals are all on spatial slices because they come from conserved charges. Okay, so that's an expression, and so I think the only part here, which if you have seen the Lorentz algebra, which it may be worth doing for you guys, is deriving this expression. So that's a good exercise in Noether theorem. Okay, because Noether theorem, this comes from space-time translation. It's somewhat easier to derive a Noether charge if it is a global symmetry, internal symmetry. But here it's actually a space-time symmetry. So because of that, the definition of the Noether charge and how, computing it is not that hard, but the expression for the Noether charge is a bit more subtle. And I think if you understand the derivation of that, I think you would have understood the symmetries in quantum field theory. So I think it's a worthwhile thing to do. Okay. So, all right, so the thing that we are trying to do now, so as I said, we have derived this temperature and the under root density matrix in sort of in a very seemingly pedestrian way first, then made it slightly more sophisticated. Now what I'm going to do is I'm going to make it a little bit more sophisticated, and I'm going to compute the vacuum state in Minkowski space, and from that compute the under root density matrix. Okay, so that's the way we are going to proceed. And the first observation, this is something that you have seen from last time, is that my path integral basically gives me, this is my tau equal to 0 line, and this is my time direction. This is Minkowski space, and so this is also equal to, so if you remember, I can time evolve for infinite time and get the vacuum state. Okay, so here let me not specify. Okay, yeah, so here this corresponds to the vacuum configuration. So that's what I mean by 0 here. So then I have d phi e to the minus se phi. Okay, so all of this is basically a recap of what we did last time. So note that one special thing is, this is phi. Okay, so this is some profile phi that I'm putting here. And I'm integrating from an arbitrary configuration, because whatever I start with, I end up with a vacuum state anyway. So that'll give me the sket, and then I'm projecting it onto this phi. Okay, so that's my phi. So this is my path integral. Okay, so as part of kind of related to this, I'll give you one more exercise, which is again worth doing, but a bit of a digression for us. Is this path integral is actually explicitly doable if you work with a free scalar field theory. So maybe you have done this already in your quantum field theory course. So let me write it down here. So there is d cube x d tau. So d tau phi square. We wrote similar things before. Okay, so this is my action. So if free field theory I can do this path integral explicitly. Okay, and this path integral is essentially the same thing as you may have done in harmonic oscillator, but split into many pieces. If you have not done it, I'm not going to do it, and you don't really need it. But it's a good exercise in getting an idea for this guy. So this is explicitly, you can write an expression, and so I will write that expression. And note that I'm not keeping track of normalizations, that as is conventional in most of these discussions. Okay, so I'll just write the final expression here. Where this delta half, it's kind of related to the Feynman propagator, but it's not quite that. So okay, so this is a path integral you can explicitly do. So if you want to see a place, I think in Tom Banks' book on quantum field theory, you can actually, I think he does it in some detail. At least that's where I did it at one point. So this is something that you can try to do if you feel up to it. Okay. So I haven't told you the machinery for doing it in great detail because we don't need it, which is about splitting it up into pieces and kind of thinking of it into, but there are various tricks also. You don't really need to think of it as a group of oscillators. You can also formally do this path integral by thinking of this as an operator and inverting and so on and so forth. But it's a good exercise to go through, I think, if you want to be a little bit more hands-on. But again, because we don't really need it, so we are not going to do it here. Okay, and it is versions of this have actually been done in your quantum field theory course or will be done. Okay, so but the point is this object, but I want to emphasize that this is not really reliant on this being a free theory. I'm just telling you that if it is a free theory, you can explicitly write it down by actually doing the calculation. Okay, but here I'm not making that assumption. I'm just making the statement that this is my object that I want to compute, and there is a path integral expression for it that I can write down. So I think this is the last thing that I'll need you to believe if you're not so familiar with various basic quantum field theory stuff. Okay, so one thing is this Noether thing, and the other one is that path integral. So the rest of all today's lecture should be okay, I think. Okay, so what we are going to do, so as I said, we are going to split our space-time or spatial slice into two pieces, this left part and the right part. And so we will write this guy, and this is what I sort of prepared you for, that I am going to tensor factorize my Hilbert space into two halves. Okay, so I will view a configuration that is specified on this entire real line as a configuration that is specified till here and a configuration that is specified till here. Completely natural. I'm specifying some function on the real line. Of course, I can think of it as a function defined up to some point and a function defined after that. Okay, so that's why I'm thinking of it as a product of two kets. But it's important to remember that this Hilbert space, and this Hilbert space are all different. So this is the Hilbert space corresponding to the full slice, which is the Hilbert space of Minkowski quantum field theory. This guy is the Hilbert space living on this line, the left line, and this guy is the Hilbert space living on the right line. Okay, so I'm writing a bra for this state, and what we want to do is we want to compute this guy. So where is that ket 0 living? No, it's not in Rindler space. It's in Minkowski space because this guy is in Minkowski space, right? So I can only project onto that. So the claim is that the left Rindler ket and the right Rindler ket together is living in Minkowski space. Okay, so this is a Minkowski state together. Okay, so the point is that the Hilbert space in the full Minkowski space can be constructed in this way. This is our essential assumption.
Is it always possible to separate separating into subregions?
In a quantum field theory, yes, but this expression is formal. So, like in quantum field theory, there is this subtlety related to the fact that algebras of observables in subregions are better defined. Observables means operators. Algebras of operators in subregions are better defined than Hilbert spaces. So the only Hilbert space that is really well defined in a quantum field theory is the total Hilbert space. Okay, so and that total Hilbert space, when it's a free theory, we know it has a Fock basis, we can do various things. When in interacting quantum field theory, we don't even know that. It's some Hilbert space which is some jungle. Okay, but the point is, operators living on this side and operators living on this side, for many purposes, behave as though there was a tensor factorization of the Hilbert space. So that's why we say that the algebra of operators on subregions is better defined than the Hilbert space structure of a quantum field theory on subregions. Yes. Yeah, that's very important actually. Yeah. Yeah, so this is that discontinuity, whether it is there. I mean, for in Minkowski space, we will be able to argue that there is no real discontinuity and various things. But whether there is such a discontinuity in the Schwarzschild case or a black hole case is really the question of whether the horizon is smooth again. Okay, so this horizon smoothness will be a topic that will come again and again and again in this course. And if it is not smooth, you call it a firewall. Okay, so the question of whether there is a singularity or if there is, how should you treat that special point is really the question of whether there is the horizon is smooth, and if it is not smooth, then you say that there is a firewall. So yeah, I mean, right. Any other questions? Yeah, so let me emphasize that one more time. The point is that this ket phi is living on the Hilbert space of Minkowski space, or the full Hilbert space of the quantum field theory living on the full Minkowski space. This phi L is living in the Hilbert space associated to scalar field theory on a Rindler wedge or a half line, and this is living on the other half line. Okay, and the point is that these two things together give you a complete basis for the full Minkowski space. All right, so and that's the reason, that's what it means meant by this sort of heuristic statement. So let me say that it is heuristic, but you can, for all purposes, for most of our purposes, you can treat it as, we'll treat it as though it was true. Okay, so okay, so right. So now what we are going to do is the statement that I made earlier, right? So this is the equation that I wrote down. Well, I mean, okay, so let me, so let me make this statement. Okay, so I have a ket living here. Yeah, this is ket living, let me not specify it, I'll just say it phi L and phi R. Okay, so this, I claim, Rindler. So I think I might use H Rindler or H eta, all of them are the same. Okay? So acting on some ket phi L. So this is how I'm going to write it, and the idea is that, so now I'm, what I'm interested in computing is a configuration where this phi L and phi R together define a phi. And I'm interested in computing the path integral from all the way down from here up to this line. Right? That's what I mean by this object. This is that picture here. So this line here is basically that thing here. Okay, so this is where this is my t equal to 0 line. So now the claim is that because of my rotational isometry that I have, the claim is that I can think of this expectation value in terms of a path integral which is done this way, by rotation. These two are the same object, is the claim. Okay, because the theory has both symmetries. So I can do the evolution with one Hamiltonian, which is basically along this, which will be a usual Minkowski time evolution, but in Euclidean signature. Or I can do a boost in Lorentzian signature, which becomes a rotation in Euclidean signature in this direction. Both are symmetries of my theory. So I can do this also. This is the claim. Okay? So if I do so note that the Hamiltonians that I'm using this for these evolutions are different. But it is okay because both those, one of them is basically just the boost generator on this half line. Okay? But the other case, it is the Hamiltonian, the true Hamiltonian of the theory. That's what I'm doing to evolve it. But both are equally acceptable because, depending on what I want to do, because because of the translation between path integral language and Hamiltonian evolution language, and the fact that both of these are symmetries of the theory. Okay? So as long as there is a Hamiltonian interpretation for path integrals, and as long as there are multiple Hamiltonians available for my theory depending on the choice of the time direction, I can always go to the path integral language in order to go from one particular description to other. Okay, so that's what really I'm doing. So the claim is that both of these are computed by the same Hamiltonian, same path integral, but their interpretation in terms of Minkowskian time evolution is just in terms of the usual Hamiltonian evolving this way. But here, the interpretation is that I am evolving from this guy to this guy and then projecting onto this object. I haven't told you what this phi tilde L is. There is a slight subtlety there that I'll explain in a second. Okay, so the point is, I specified something here, and I'm then evolving by an angle of pi, and I project onto this, then I get the answer that I want. Okay, so this is what, so both are, the same path integral can be interpreted in two different ways. That's the statement. Okay, yeah. Can you repeat, sorry?
The rotation for the Taconian in the first time.
The rotation for what?
In the first time.
This one, yes.
Rotation for the Taconian.
Here.
It means that there are two Tacons, one is COL and one is
No, that's a good question. So this is basically the Minkowski vacuum on both sides. Okay, so this is the Minkowski vacuum in Hilbert space of the Minkowski. It's the Hilbert space of the full field theory living on the Minkowski space, and the vacuum of that is this guy. And here also it's the exact same thing, but here I am projecting it onto some random state in that same Hilbert space. But here I am thinking of that in terms of two separate states in two of these Hilbert spaces. But it's possible to do that because my Hilbert space admits a natural tensor factorization. Okay, so that's why I am allowed to, or I can do it. Otherwise I cannot do it. Okay, so yeah, so the fact that I can project from my Minkowski Hilbert space onto a tensor product of two of these Rindler Hilbert spaces is possible because of this fact. Okay, so that's how I'm doing this thing here. Okay, so this is, now let me explain what this phi tilde L means. So before that, let me emphasize that this integral is over the entire spatial slice. Okay, so that's a property of all charges in Minkowski field theory. So you have to integrate over this entire spatial slice in order to get this boost generator. Okay, so yeah. So the statement that I'm making now is that this boost generator is, I'm only going to integrate it from one side, only half side, in order to do this Rindler Hamiltonian. It's not the full Hilbert, boost generator, because what I'm doing is I'm starting from here and evolving like this, right? So this is my spatial slice according to this picture. So which means that I am going to compute my charges in that half slice. Okay, so here I am integrating only on x less than 0 or x greater than 0 depending on which side I'm starting from. Okay, so that's a small point, but it's again related to this question of the smoothness of the point where it joins. Okay, so yeah, so let me write that explicitly where H Rindler is nothing but kx, but integrated only on the half line. On the half line. Okay, so because my time evolution is like this here, and remember that the definition of time is that this is where I'm putting the ket, basically. Oh, did I do that here? Oh. So I think I screwed that up here. That is going to cause a huge amount of problems for me. So phi r. I think I called one of them phi and phi tilde L. So this is R. No, this is fine. Yeah, good. So otherwise this would have caused a lot of unnecessary heartache. So on this I am basically defining my, because the time is coming this way, this is the ket, right? So here my integral is basically on the right half line. That's all I wanted to say, because if it is on the left half line I'll have to flip various.
So this H Rindler is not the full
No, H Rindler is only over this guy, because it's the charge that I'm associating to rotation on this guy. So this is my spatial slice, right? So if I have a rotation, if this is my time evolution, this is my spatial slice, or this is my spatial slice. And if I want to look at it, I can also phrase the charge in terms of here, but since the time is coming this way and this is more natural, like as I said, this is the natural ket. Here it would be a bra, so that causes some unnecessary issues. So here, unnecessary complex conjugations and things like that. So here, I can just define my integral on this spatial slice, and that gives me my charge. So that's the one that I'm integrating over. So you understand the point. This is the time evolution direction. The time evolution is not happening along this direction, it is happening along this. So the spatial slice is only a half line. So that's why the charge is getting integrated only on the half line. Okay, so, and the second point is that where this phi tilde of L is the CPT conjugate of phi L. Okay, so how much energy do you have? Are you all completely wasted? Because this will take some cojones from you to hold on. You're already destroyed. So, okay, so maybe it is a good idea to stop here. We'll come back to it. Okay, because there is a lot of, there's going to be a few flips of signs, but so if you understand this, I don't think there is nothing else for you to understand. This lecture and the next couple of lectures, if you understand well enough, I think the rest is all sort of more or less trivial. So this is kind of, we have sort of completed some ascent. You can turn it off if you like, yeah. So I think, yeah, so it's a